Thank you, Rahim. Thank you, Dr. Al-Gardi. It's a very special pleasure to be here. Good morning, namaskar, salam alaikum, and bonjour, and let's get started. We have some questions from the audience, and there are some other questions also which my students often ask. So we'll see how things go. I like to show the oil price and gas price. You can see things are going up. You see that? Oil price, gas price. And you also see in the corner a very interesting graph. It shows the shale production in the US. The black curve is the one which is the big shale reservoir. Okay, so first we'll take these questions. In situ combustion, which we receive from some of our guests. And let me put it this way, that my answers will be brief, because we don't have a lot of time. But some of these questions are quite complex, and I could go on for half hour answering them, but I'll keep my answers very brief altogether. And if you want to have any explanation, please let me know. Okay, the first question is in situ combustion independent of depth? Depth, how much is the depth? Well, the deepest in situ combustion we have done was in about 10,000 feet, 3,000 meters. So what is the problem with depth? Really, we don't have any special problem with depth in situ combustion because we are injecting air. The only thing to remember is that permeability goes down as the depth goes up. As you go deeper and deeper, permeability goes down. So there may not be enough high permeability, number one, to support the air injection rate required for the reservoir, or to support the combustion advance for that permeability and for that air injection rate. So that is the only depth limitation. You have to be careful that we can inject air at a high enough rate at the available pressure. And secondly, that the permeability allows the advance of the combustion front. Now, we didn't go into the calculations of that, but that's the general idea. Are we able to, second question, are we able to expand the combustion zone, more expanded, generating more steam and displacing more oil? Okay, the idea here is this, that we have is geometry like this, and the front is a very thin rim. It's a rim, R-I-M, rim, ahead of the burning front. So the question, as I understand, is that if we were to inject water with air, then will it pick up the heat which is inside this burn zone? This is all burnt sand with a lot of heat in it. So the water will pick up the heat from the burnt sand and change into steam, and the steam will further give you a drive, which is shown by this next circle. So the answer is yes. The only limitation is this, and you have to be very careful about it, that the theory says that the water and air travel together. They must be together. But what really happens is the water tends to go down, air tends to go up. So you have to look at the gravity segregation problem. If the vertical permeability high, the process won't work. So the general answer is yes, but subject to the gravity segregation of water. What can we do to overcome the gravity segregation of air? Well, that is a difficult problem, let's put it this way. As I said before, that lighter fluids go up and air is much lighter than water or the oil or the fluids in the reservoir. So the air will go up. Can we make it go down? Well, what people do is that they try to inject air lower in the reservoir and hoping that there'll be at least some period where the air and the air will be essentially covering most of this cross section of the reservoir. But the reality is that the air goes up like this. And the combustion front, instead of being a vertical zone, as I have been drawing sometimes, is really a horizontal front like this, which means that you need to have much more air to support that huge surface. And we cannot do it often, and the combustion becomes extinct. In other words, the fire goes out. So really, there's not a whole lot we can go to overcome gravity segregation of air. Now, people have suggested the injection of foam with air. That's a different kind of a problem. It has been tested, in fact, but it's not very successful. Foams often don't form even, or they break up very soon. Okay, next question. What is an injectivity test and why is it important regarding the air injection rate? Well, this is a very important test, air injectivity test. So let's say you're given an oil, you do the fire tube test, and you do all the kinetics. And as a result, we'll have a very important number, and that is the minimum advance of the combustion front. In other words, if it doesn't advance at that rate or a higher rate, the combustion will go out or the fire will become extinct. So injectivity test will tell you, can you inject air at a high enough rate to support the combustion advance? Many times it's not enough. So combustion cannot be done. I have several experiences like that. Now, the other part is this, that the injectivity test, generally it will take maybe a week, 2 weeks. In that time, sometimes you may have spontaneous ignition. You have to watch out for that. Spontaneous ignition means that we are blowing oxygen on a hydrocarbon, and the hydrocarbon will catch fire eventually. If you take a bit of gasoline in a cup and blow air on it, it will catch fire after even a couple of minutes. We did this experiment at the lab to show the students once. So injectivity test may cause spontaneous ignition, which is a complex problem because spontaneous ignition does not occur around the wellbore. It occurs a little bit far out, and there is reason for that. And then after that, as you inject air, the front will actually first move backward, like in reverse combustion, and only when it reaches the well, then it starts moving forward. So it's a complex process, and you have to be careful. So to answer the question one more time, injectivity test is important to know whether we can inject air at the desired rate. That will determine also what kind of compressor you buy. But at the same time, keep in mind that the air injection may cause spontaneous ignition in the reservoir. That's a big question by itself, how you tell whether it occurred and what do you do about it and so forth. Okay, the next question is, what does the term low temperature oxidation mean in situ combustion, and why is it a big issue from the reservoir point of view? Well, it's like this, that let me see, I have maybe a blank sheet here, that's easier. If we have the oxygen temperature here, temperature on this, and the air rate, let's say, flux, then the combustion process looks like this. At a low rate, wait a second, I made a mistake here. The temperature should be on this scale. The air flux be on this scale. So at a certain air flux, you'll have low temperature oxidation in this range, and this range will be about, say, 300 degrees C, 250, 300 degrees C. And then as we go higher, we'll have high temperature oxidation, and that will be 450 to 700 degrees C. And then there's a region here which is where you may have a what we call a cooling effect. So we don't want to get to either of these. We want to operate in this region. Low temperature oxidation essentially means that even if you inject air at a low rate, it will still react with the oxygen will react with the oil, hydrocarbons. And low temperature oxidation will produce a whole range of products. It will produce oxygen additive, O2 additive products. O2 additive products means alcohols, ketones, ethers, and whole aldehydes, and a whole lot of other products which react with the oil and produce solids. In other words, asphaltenes and rosins will drop out and plug up the formation. That is the problem with low temperature oxidation. And that is a very serious problem, even when with a high temperature oxidation where you're operating here, because the front is not exactly circular, you'll have portions of the front at low temperature oxidation, and that part of the front will become extinct because it will block the air. Now, high temperature oxidation gives you theoretically only CO2 and CO and of course water. So that is a huge difference between LTO and HTO. We try to avoid LTO, and if you do have LTO, you really cannot do much to correct it. So LTO is the end of the process actually. I just had a field test in Colombia, and that's exactly what happened there. Is quench combustion feasible? This last question. Quench combustion means that we are injecting so much water that the fire front actually goes out, becomes extinct. And then what happens is that we expect that the air will go farther out in the reservoir and start a new fire front. So in other words, the picture looks like this. Draw it here. If we draw the temperature here, distance here, then initially we have fire front. I'll make it very simple looking diagram like this. Let's say this is the reservoir temperature, the x-axis is the reservoir temperature. Okay, so when you start the process, it looks like this. Now we inject a lot of water, it puts out the fire, and it takes the heat further out. It looks like this. And now more oxygen is coming. It will react at this point, create a new combustion front. And then we inject more water. It will put all this out and we'll have a new heat wave. So the process becomes a heat wave process in a quench combustion. And you'll have quench combustion if you're injecting in the range of 1,200 barrels per million SCF of air. From my experience, it doesn't work. In the field, we don't have a nice, clean geometry as I showed you in the diagram. So you can try it, but what happens is that it becomes just a water flood. We had at least one field test in Venezuela in the 1970, 71 period, when they were able to achieve quench combustion. Here are a couple more questions. In the US, there says there are almost 500 UR surfactant flooding projects, but none of have been successful. So they want to understand what is the problem. Well, the problem is this, two problems. Number one, you have to inject a chemical. Chemicals are expensive. Number one. Number two, the chemicals will react with the rock and there will be adsorption. Adsorption means that the chemical will essentially stick to the rock. How much adsorption occurs? Maybe 1 gram, less than 1 gram, sometime even more, per gram of rock. Okay, so if you have 1 acre foot of rock, 1 acre foot of rock weighs 6 million pounds. Okay, and maybe your pattern size is 5 acres, maybe the formation is 30 foot thick. So that becomes 150 times 6. And that becomes 900 million pounds. Now, if your adsorption is 1 milligram, sorry about that, 1 milligram per gram of rock, then divide by 1,000. And your adsorption loss alone will be 900 times 1,000, 900,000 pounds. So 900,000 pounds of the chemical are lost to the rock because the rock has a huge surface area. As I told you, if you have a sugar cube, the amount of surface area in that little sugar cube will be the size of a full big screen, like on a movie screen. So that is the kind of surface area we are dealing with. So we are losing 900,000 pounds just to the rock, and then maybe you need another 900 to do whatever you want to do with the chemical. Maybe you want to create a miscible front or something like that. So that is the big problem, the cost problem. Of course, I mentioned in number one, and then the adsorption problem makes it worse. And the third problem is the pattern size. Typically, now I've worked on 35 or so field tests. The pattern size in these field tests was never more than 5 acres. And the reason is again very simple. Now we are looking at a different kind of problem. Here is the pattern. We are injecting the chemical here. And as the chemical going, it's not going in a circular fashion, it's going like this, like this. As it advances, it becomes less and less concentrated. In other words, it's diluted by the water. It spreads out. Velocity is also becomes smaller. So adsorption actually increases, loss increases. So the pattern size typically is very small. Actually, some of the floods we did were only on a 1 acre pattern, which doesn't make any sense, but we were doing research. But in a practical sense, 5 acres is a typical pattern size. You may try 10 acres, but you may find that it doesn't work. For polymer flooding, they even have a much bigger pattern size, and they were failures. I know one which was a huge size, something like 150 acres, and I told those people that it's not going to work. Anyway, that's a different story. So the pattern size means that you have to have many more wells, and that increases the cost. So those are some of the basic problems in chemical flooding. Now, the other question is that in the case of China producing 170,000 barrels per day in Daching, well, Daching or China is a different story. In China, cost is a much smaller factor than, say, in the United States or Canada or other countries. We do something only if it makes money. So you can see that in the US, there's practically no chemical flood. I mean, there may be a small one here and there. Whereas in China, the chemical flooding, which is polymer, as well as ASP, as well as now they're doing the surfactant polymer, they're producing that much oil. I've been to Dacheng field 3 times. Question, are they making any money? But they will tell you yes. But if you look at the concentration zone and the spacing of the wells, you'll say that it couldn't be possibly economical from our point of view in America. Okay, what is the next question is what is the mechanism through which we create ignition? Well, ignition means that we have a formation here. It's the injection well, it's the production well. We are injecting air and we want to ignite the reservoir like this. How do we do that? Well, first of all, as I said a minute ago, you may have a spontaneous ignition. The oxygen in the air may react with the hydrocarbon here and create a combustion front. That's one possibility, and that's a very complex process. Spontaneous ignition, however, is often used. Now, the second mechanism, the mechanism is, of course, oxidation of the oil. And you can do it by an electrical heater, actually, not pulse. Pulse will be too short. Electrical heater is hanging there. I've done this in the field. So imagine that you have an electrical heater here, long heater, maybe 20 foot long, and it's hanging in the well and heating the oil, and it's hanging there maybe for 12 to 24 hours. So it's not a pulse for a long time while we are injecting air. And eventually you will start ignition and pull the heater out. And still another technique will be instead of heater, electrical heater, you use a gas burner. We have done that also. And you have to be very careful that if you have a gas burner, the gas flame does not hit the casing, otherwise you'll melt the casing. So we have a gas burner with the flame sufficiently shielded. Okay, so we do that also. Still another process which is actually my favorite, if it is workable. You know, in some situation only one method will work, and that is to inject steam. So inject steam for maybe a week or a few days, and that will create a high temperature zone here. And after that, inject air. So what will happen is that the air will react with the oil at a temperature of about maybe about 200 degrees C, 250 degrees C. And as you know, the oxidation is a self-accelerating process. So eventually, that part of the formation will have ignition. So those are the choices, and all are, as I say, have their own problems, and they're not all applicable. So you have to look at the reservoir carefully and choose the right process for ignition. If you do not have the right method, you may actually lose the well. I have that experience too one time in Venezuela. Okay, the last question is, in reverse combustion, the ignition occurs at the producer. But how can the combustion front overcome the pressure of the injected air and propagate in a direction opposite to it? Okay, it's an interesting question. Let me use some space here. Let's say we have, this is our formation. This is the injection well. This is the producing well. We are injecting air here. Air is going this way. And we are igniting here. So combustion zone is ignited here. Now what's happening is that the air is advancing, and you will say that, you correctly say that the pressure gradient is this way. Delta P is this way. So you'll say that, okay, the fluids cannot flow. But what's happening is this, the combustion front is advancing this way because it is seeking oxygen. So combustion front will go where the oxygen is. And as the combustion front advances, it will also drag the fluids. So as a result, the lot of fluids will stay here and they will be at a very high temperature. And also at the same time, the oxygen concentration is going down as the oxygen advances because it's being consumed in LTO, low temperature oxidation. So eventually the front goes out unless the spacing is very small. In a couple of field tests, which were essentially research projects, the pattern size was only 1 acre. They kept these wells very close together so that the combustion front goes all the way to the injection well. And it more or less did, but the process didn't work nevertheless. Okay, so we took care of the questions here. Now we'll go to the Q&A area. And the Q&A, I'll open that up. Okay.
Do you need my help?
You can, if you want, you can ask those questions. I can read them also here. I mean, you can read them, Rahima, if you want. Somebody asked me if I've been to Pakistan. Yes, I've been there. So what do you want to do, Rahima? Do you want to read this?
Yeah, I'm gonna
like the first question. I want sites and sources where I can find information about underbalanced drilling. Well, lot of sources. If you just type it in Google, you'll see that underbalanced drilling. I've done it in the field. And there's an awful lot of literature on it, whole books on it. So you go ahead, Rahima, if you want to read the next one.
Okay, thank you. If during the in-situ combustion, most of the reservoir is cold, with the exception of the burning front, why is it believed that high temperatures can lead to the well equipment damage?
Yeah, well, it's like this. Let me see if I can get a blank screen here somewhere. Yeah, okay. Yeah, the question is that if we draw that formation that I keep drawing all the time, and this is the producing well, and this is the injection well. What I'm drawing here is a cross section of a 5 part or something like that. Okay, correctly, the high temperatures are here. Let's say I'll draw the vertical front here. As I told you, the fronts are more like horizontal, but it's easier to explain. So this area is very, very hot. And combustion zone is the hottest, maybe 700 degrees C. The hot zone is maybe 200 to 300 degrees C. Okay, but the rest of the reservoir, well, there's a steam front here, there's some heat there, but the rest of the reservoir is still at, let's say, 30 degrees C. So if we could maintain that situation, things will be wonderful because this front will advance, it will push all the oil, and only when we have produced all the oil, the front will reach here, and then we'll shut the whole thing down. But now my picture is not correct because the combustion front is not like this. The combustion front is really like this. And you can see that the air, much of the air is going on the top here, and the combustion zone is way spread out over the reservoir, and it arrives at the well bore way before we recover most of the oil. So what happens is that we have very high temperatures in the well bore because we are producing this hot zone is right here, and the air is coming. We have a lot of gas, but some of the air is pushing the oil also. So it's a very common problem that the well is very hot, but we are continuing to produce the well because we're producing oil. Actually, to make things even more complex, we are injecting water into the well bore of the producer. So there is a spaghetti string. A spaghetti string is maybe a half-inch tubing, and we are injecting water into the producer while producing the oil and everything. So water goes and cools the well, and we are producing this hard zone. So to answer the question that we are, oh, the question was above that. Sorry. Yeah, this is the thing that we have heat breakthrough way before we finish the process because of the overlay or the gravity segregation of the combustion front. Okay, so next one.
Thank you. The second question is, why is it necessary to provide enough air for the complete burning of fuel content during in-situ combustion? Will the burning front stop if the fuel is only partially combusted?
Okay. Well, it's like this, that to simplify the answer, imagine that the combustion front is a piston, ideally. It's like a piston which is pushing everything ahead or burning everything ahead. So you see the combustion front is pushing oil and water and gases ahead. And at the same time, some of the oil is remaining in cracking and creating the so-called fuel or the coke to burn the front, to keep it burning. So what happens now is this, that if you cut down the air, the combustion front cannot advance at the rate required, and eventually what will happen, it will go out. The combustion front must move the minimum velocity. Minimum combustion zone velocity is 1.25 inches per day. This is the minimum combustion zone velocity. Inches per day. So you must have enough air to support that velocity. Otherwise, the combustion zone will go out. Okay.
So, thank you. Another question is, for steam injection, is there any screening criteria to choose CSS instead of steam flood?
Yes. For a steam injection, the most important difference between CSS and light oil or medium oil is that the CSS will respond in more viscous or the heavier oils. So if your viscosity, oil viscosity is several thousand centipoise, probably CSS will be successful. If it is less, it may still produce some oil, but it won't be as good. Maybe you'll be better off doing a steam flood. CSS is a fairly forgiving process. You understand me? Forgiving means that even if the conditions are not right, it will still produce some oil. A steam flood is also like that, but CSS is much cheaper in a way because you're injecting steam for a small amount of time and then putting the well on production. So to answer the question again, that the oil viscosity should be relatively high for CSS to succeed in the range of several thousand centipoise. But then, you know, steam flood may be applicable also in 1,000 centipoise or even in sometimes a little bit higher viscosity. In any case, after CSS, we try to do a steam flood, not always, but most of the time. So again, CSS, in light oils, you cannot do CSS at all. In medium oils, sometimes you can do CSS, although it may not give you such a good response. So that is the answer to that question.
Thank you very much. Our next question is, what is the maximum depth recorded for a commercially successful steam flooding project?
That is an interesting question in the sense that there is a maximum depth where steam will be more successful. Let me put it this way, that most of the, just about 90% of the steam projects are in depths less than 3,000 feet. 90% of the project. 3,000 feet or 1,000 meters. If the reservoir are deeper than that, you can still try steam injection, but what happens is that you need a higher pressure will be high, and then what happens is that the latent heat of steam will be low. Latent heat of steam, LV, is a very important number because that's what causes the formation of the steam chamber or the steam zone. So high pressure needed for greater depths will lower the latent heat, and also the steam will behave more like hot water. Hot water is being used in a deep project right now in one of the projects. It's an experimental project. So you can use hot water at any depth, but it may not be as successful because it doesn't have latent heat. So to answer the question one more time, simply that the depth should be less than 3,000 feet. Now, I should also mention that if you have a deeper steam reservoir, you can still inject steam, but you'll have to mix a gas with it. So for example, you can have a mixture of steam and nitrogen, and you can inject it into a 10,000 foot reservoir, because you can see that if you mix of steam and a gas, we have 2 degrees of freedom. We can fix the temperature and pressure separately. Otherwise, if you have steam only, you know, it's a property of steam, the pressure and temperature are tied together. If you fix the pressure, temperature is fixed. Okay, you have no way to separate them. But if you have a gas with steam, you can separate steam and steam pressure and temperature. But I should also mention from my experience, those projects are quite problematic. I don't know any commercially successful project. The possibility is there, however. Thank you.
Thank you very much.
Okay, that is the answer.
Thank you. Other question is, as mentioned in the session, most of the in-situ combustion projects are not commercially successful. So what is the item that raises the cost of this method? Or is it the compressors or the periodic workover for the repeated mechanical problems? And what is approximately the cost of barrel of oil in this method?
The answer is all of the above. You understand? All the things you wrote are the problem. Well, if you remember, one of my slides shows all the problems. Okay, if I separate the problems, the biggest problem are the mechanical problems. Mechanical problems mean that we are producing a very large amounts of gases. We are operating at a gas oil ratio of maybe 10,000, 15,000. Actually, in one project, I saw a gas oil ratio of 100,000 SCF per barrel. But typically, you are operating at 10 to 15,000, and you know that's no good. SCF of gas per barrel of oil, okay, or about 5,000 cubic meter per cubic meter. And that gas will cause erosion problems, sand production. It will actually cut holes into your casing. And then you have to handle all that gas at the surface because it's toxic. So mechanical problems, and there are other mechanical problems too, which I am not, temperature related, high temperature. Okay, the other very huge problem is that we cannot control the front. Front control is very difficult in in-situ combustion. The fire goes where it wants to go. And the reason is this. As I showed you in reverse combustion, that the combustion zone advances in the direction of the air because there is oxygen in there. Well, in an in-situ combustion project, the front goes where there is fuel, which is oil. So if the oil saturation is high, the combustion zone will be pulled toward that. And so control is very, very difficult. Okay, the other part of the question is, what is the cost of per barrel of oil? I would say, from my experience, in the more successful projects, cost was something like $20 per barrel. So if your heavy oil is, let's say, $30 a barrel, then you're still making a small amount of money, but that cost goes up as the project goes on. Things get worse. But in a sort of average sort of way, I'll say that if you have a partially successful combustion project, which is making a little bit of money, maybe I know about a dozen, maybe 12 projects of that in that nature, then the cost will be about $20 a barrel. Thank you.
Thank you very much. Another question is, in the context of cyclic steam injection, why are the producing rates low? Is it a matter of reservoir depletion or the operation itself?
Well, is the nature of the process. You see, here is the well bore, and you imagine this is a plane view, and imagine that the whole board is the reservoir. Now we inject steam, and we heat the reservoir to this temperature, to a high temperature, to this radius. So that circle is a high temperature zone where the oil viscosity is reduced to maybe 1 centipoise. And after that, we produce this well. So we produce this well, and this part of the reservoir will have a increased higher than the original water saturation. So we are essentially injecting steam, producing oil, and then we are leaving the water behind, or much of it is left behind, maybe 70%. Okay, then we go to the second cycle. In the second cycle, there is less oil there because there is a lot of water. Some oil is also coming from outside, of course, but there is less oil. Definitely the oil saturation is lower. So in the second cycle, we have less oil for the same amount of steam, and so on. So as we go on from cycle to cycle, we tend to produce less and less oil. So if I produce the oil production rate versus time, the first cycle will look like this. Then you inject, shut the well. Second cycle will look like this. Third will look like this. And it goes like that. How fast those cycles go down will depend on the reservoir. Some of the reservoirs, like the tar sands in Canada, you can go to many cycles, and the production rate, well, it goes down, but not that rapidly. In Venezuela, you're lucky to do 3 cycles. First cycle is extremely good. Second cycle is relatively good. Third cycle is very poor. And then they stop, go to the next well. Thank you.
Thank you very much. Another question is, which one of the non-Newtonian fluid behaviors is desired in polymer injection?
Okay, give me 1 second because my computer needs to be plugged.
Okay, sure.
Okay, now things are better. Which one of the non-Newtonian fluid behaviors is desired?
In polymer injection.
Well, let me put it this way. Really none. But the polymers are by nature non-Newtonian. And I would say that in general, the viscosity increases with shear. So the shear thickening usually You really cannot change it much. The only thing you can do is that there are certain polymers which will actually gel. They'll make a gel in the reservoir, much like a drilling mud. In other words, they're thixotropic. If that is the case, then you have to be very careful. Do you want that kind of a behavior? It's not very desirable generally, but you may want to inject the polymer very late in a water flood, in which you will want some gelling effect. But to answer the question, really, we don't really want them to be non-Newtonian, but they are non-Newtonian. They are shear thickening generally. We don't have much control on that.
Thank you very much. Another question is, as mentioned in this session, most of the chemical flooding projects are not commercially successful. What is approximate the cost of barrel of oil for each method of chemical flooding?
Well, first of all, you have to decide whether the chemical floods are, whichever method you are choosing is actually producing any oil, maybe it's producing nothing. But just to give you an idea, for polymer flooding, if it works, polymer flood is used often at the end of a water flood or during a water flood, and the cost is typically 5 to 10, let's say $10 a barrel altogether. But the recovery factor is quite low. The recovery factor, RF recovery factor, is maybe only 5%, or sometime even less. But given the data, we have done thousands of polymer flood. One of my friends who is an expert in polymer flooding, he designed 350 polymer floods. I myself designed about a dozen. And well, none of them really produce much oil. They produce less than 5% oil, additional oil. And the cost was higher than $10 a barrel. But $10 is a good number based upon my friend's experience with polymer flooding in Texas mostly. Thank you.
Thank you very much. We have another question about Miscible ER. So it is like, what can you say about the relevance of the Miscible ER?
Miscible ER.
Yeah.
Sorry, is it in the chat or not?
It's in the chat, yeah.
Somehow this chat box is not working on my computer.
Yeah, the question was like, what can you say about the relevance of the Miscible ER?
No, I mean question answer box. Is it in the question answer box?
No, it's in the chat.
Oh, it's in the chat. Okay. Just give me one.
If you go up, it's one of the first questions.
Yeah. Okay, now I see it. Okay. Just a second. Okay. I don't see that running now, but will you repeat the question, please?
What can you say about the relevance of the Miscible ER?
Immiscible or miscible?
Miscible.
Oh, okay. You know, that's one topic we didn't discuss. Miscible ER. That was the topic on which I wrote my PhD thesis, so I know the miscible ER rather well. We didn't have time, that's why we didn't cover it. Okay, miscible ER. Miscible methods have been used widely. I have to tell you this very quick story. In 1956, I don't know whether any of you remember that. In 1956 was the Suez crisis. I hope the people from Egypt remember the Suez crisis, when the French and the British took over the Suez Canal and they shut it off. So Egypt sank some ships in the Suez Canal at the time to block it. And finally, they beat out the British and the French from the Suez zone. And then it took time to clean it out. But anyway, 56 was when the miscible displacement became very important, because the US oil companies, they got together and they said miscible displacement is the way to go. We didn't have any steam at that time, by the way. We didn't have any, much combustion success. So they said miscible displacement is the thing to do. So they did many miscible projects. 110 miscible projects were done in 1956 to about 1970 period, and hardly any of them were successful. Most of them were miscible slip, where we injected LPG or propane, but many of them were high pressure gas injection, lean gas, and also rich gas. Now, much later, 1972, carbon dioxide came. When actually at Penn State, Pennsylvania State University, where I was there for more than 20 years, we did a lot of work with CO2 in 60s, 1960s. We did phase behavior studies, we did lab tests. And in 1972, Chevron started a miscible flood in the Sackrock field in Texas. That is still running. Would you believe that is still going on? CO2 behaves like something like between propane and ethane, and it behaves like a miscible solvent, but it does not become miscible with the oil right away. It has to go halfway or some distance in the reservoir before it becomes fully miscible as a result of phase exchange. So let's put it this way to answer the question quickly. Miscible displacement has been partially successful, especially where we could get over the gravity override. In other words, you do the miscible flood vertically. We have several field tests like that. Now, other than that, CO2 has been successful in something like 200 reservoirs, and all the CO2 flood, except for one or two, all of them are in Texas, and they are in Permian Basin. Why? Because there are two big CO2 reservoirs. In Permian Basin in Texas, there are two reservoirs which produce only CO2. Can you imagine that? So CO2 is very cheap. So here is the rule. If CO2 is free, then you can make money with CO2 floods. Or let me put it this way, that is no longer free. It used to be 4 or 5 cents a SCF. Now it is not free at all. It's almost as expensive as natural gas. But if it is readily available, so let me put it this way, that if CO2 is low priced, and if it is readily available, then you can make money with CO2, as we are doing in Permian Basin. But if you have to collect CO2 from different refineries, cement plants, and God knows what, then it probably won't make any money. That is the state of the miscible displacement.